Good afternoon, ladies and gentlemen. I am Ntsikelelo Charles, currently a second-year master's student in the field of cosmology. Today, I'll be sharing with you a summary of my research project, and I hope you'll find it interesting. Now, we know that humans are by nature ever curious. We wonder about our origins and that of the universe. This is just one of the deep fundamental questions of humanity. And indeed, we also live in an era of advanced technology, enabling us to ever get closer to answering these questions. Now, the Big Bang Theory is one study field that attempts to uncover the origins of the universe. Our understanding of the universe is that it began with an explosion around 14 billion years ago. The temperature during this time was extremely high, billions of degrees high. Now, like an inflating balloon, the universe expanded and in the process it also cooled down. This allowed stars and galaxies to form and thus emitting light to their surroundings. The emitted radiation from the first stars and galaxies was absorbed by the surrounding gas. Now, the surrounding gas also emitted light at a particular frequency. Now, how this process unfolded is least known, particularly from an experimental point of view. Various cutting-edge radio telescopes have been built all around the world with experiments in search of the light from the first stars and galaxies. There are, however, difficulties faced by these experiments with varying degrees of complexity. The most common, often faced by all these experiments, is the presence of brighter emissions alongside the signal of interest, mainly coming from our own local galaxy, the Milky Way. The radiation is about 10,000 times brighter than the signal of interest. Now, there are ways to get around this problem. One can subtract the bright radiation from the galaxy, or one can define a quantity that will enable them to avoid galactic emission altogether, enabling one to isolate the signal of interest. Now, both of these methods rely heavily upon the ideal behavior of the radio telescope. However, the behavior of the telescope is far from ideal. Imperfections are always present. Now, the goal of my research is to find out to what extent should we actually worry about radio telescope imperfections in validating our methods of isolation. We narrowed our research and focused on the avoidance method rather than the subtraction. So I simulated various observation scenarios that included looking at different patches of the sky. Now we find significant results. Firstly, we found that different patches of the sky actually yield different results. We expected this to be the case. However, the degree of deviation was alarming. We further characterized the main differences between the sky patches. We found that, contrary to common understanding, it is actually better to point the telescope directly at the strong galactic emission in order to better one's chances of separating the signal. We hope that this result will contribute to scientific knowledge of the universe, and I thank you.